Yes. So today lecture I am going to talk about a very interesting question in the subject of mathematics. Maybe this subject not only is part of mathematics, but it somehow interlaces or it interfaces or it's on the borderline of many subjects. Maybe historically, philosophy has been a precursor to addressing this fundamental question. But in the meantime, if we identify it in 20th century or 21st century, theoretical physics, mathematics, empirical sciences have been. So the question is whether mathematical truths are empirical or a priori or they are intuitive. So these are three broad categorifications or categories how mathematicians normally work if as different schools or as operative as mathematicians, and they have the why. So if whether mathematical truths are empirical or they are intuitive or they are a priori. So these constructions stem from fundamental philosophical assumptions from philosophy. So whether our world in which we are living, whether the truth content of the things which we observe, it should be only based on our sense perceptions, which is part of how we define empirical and the logic which it supports, or there are intuitive prior assumptions which go into making of them. So, right from the time of Aristotle, so if I read or mathematical, or so I will just we'll start with mathematical truths, but we maybe the focus will be more on the. We'll try to just make it more part of the geometrical statements. Mathematical truths in general sense, geometrical statements in some particular sense. So whether are mathematical truths empirical, intuitive, or a priori. So before if you write from ancient times, if you just take Aristotle or the school of Plato or Pythagoras, so the sort of debates which got crystallized in the ancient times is, for example, for Aristotle, you might have heard of something called analytical statement. And synthetic statement. Okay. So analytical statement, you know, analytical statement is any statement which has a subject and which has a predicate. So or a premise. So we can trace the logic of a given statement to its premise, the original statement, such that what you want to infer or what you want to deduce from the primary statement, there is exact mapping. There is not something additional to it, or there is not something less which we can add to the primary statement. So the secondary statement follows from the primary statement, or it's contained, the logic of the secondary statement is contained in the primary statement. This is an analytical statement. Synthetic statement means that the primary statement has more than one proposition or one assumptions which is embedded in it, but in the process it will also explain the secondary statement. So the primary statement will have more to it, more assumptions to it, and those assumptions may or may not be empirical. So from this statement, If you just trace this question to how various philosophers, whether it's Immanuel Kant has been a very influential figure in how he, if you read his critique of pure reason, his how he tries to say what mathematics is all about. He talks of something a priori and posteriori statements. So mathematical truths are a priori statements of space and time, and and uh, and uh, and if there's Kant, there is Brouwer, there is Wheel, there are many mathematicians and philosophers who can categorize the distinction of mathematical and analytical and synthetic statements in different categories. So if there are broad before how we can characterize analytical and synthetic statements, we have to first see. So, in the body of mathematics, if we say how to define mathematics, so there can be. So before we are going, so I'll just suspend this question for some time because how if mathematical statements or mathematical propositions can be somehow constructed from these analytical or synthetic statements. So they can be classified in these two statements. So from this, how do different schools of mathematics give this category? So before that, so I'll give a brief account of there have been in mathematics there are formalists, there are intuitionists, and there can be empiricists, or sorry, there can be third. Logicists, or you can also have how these three schools of thought, how they will construct this empirical world, the world which we are observing with our senses, and the logic which it supports. So so who are formalists, who are intuitionists, and who are logicists? So to each school, there is a whole class of mathematicians who have been engaged with this question fundamentally, what is mathematics? So even a lot of mathematicians will disagree with this very content, whether philosophy of mathematics should be a subject or not. They will answer that mathematics is you do mathematics, you don't say what is mathematics. So this is also, or if you quote Von Neumann, he says that mathematics we become used to some things rather than understanding them. So these different approaches of approaching mathematics have stemmed from different approaches of seeing things. So for formalists, mathematics is a game of formal structures, and to impose some rules of formal reasoning on those formal structures, and we arrive at some other statements, and there and then off. And in this school, maybe there are various mathematicians. I don't, if I don't remember their names. So maybe, I mean, so there are various mathematicians like formalists, you can say. So in the same way, there are logicians. Logicians are of the view that the whole of mathematics can be reduced to logic. The logic, they take logic, the prior existence of logic means how we can, how the rules of reasoning is there, and how the rules, how we impose those very rules of reasoning. So that is the fundamental edifice from which whole of mathematics can be constructed. Arithmetic, statements of arithmetic, statements of geometry, statements of algebra, So in this school there have been Russell, there have been Frege, there have been Whitehead, so many other people. In the formalists, maybe there are Brower, there are other schools, and then you have also this is intuitionists. Intuitionists are of the opinion that the truths or the statements of mathematics are so they are prior. They exist eternally in our what I should say subconscious or our intuition. So that intuition is not necessarily to be had from the physical world or from the its justification cannot be had from what we are going to observe. So its justification is from prior notions which are intuitive or which are innate. So how? So if these are so maybe people like Brower and other people they are belong to this school. And pertinent to mention is, for example, you might if you search through the literature like this law of excluded middle, law of contradiction, which are the basic premise. For example, A is equal to B is equal to C, so E is equal to C. So these, if you just see the arguments which are constructed by intuitionists, they will say this statement will hold only in a certain time. So there, if you take temporal aspect of time, for example, a statement which is evolving in time, you can never prove this law of excluded middle within the Aristotelian logic. So they have their own way of seeing the foundations of mathematics. So now this is the historical, this is the bit, the methodological part of it. So the point is, how do these three schools of mathematics view so empiricists, I say that so primarily mathematics as a game or as a construction is involved in its motivation is not entirely empirical. So here we just categorize sciences particularly, theoretical sciences, physics and other things. In mathematics, we normally there is part of empirical world attached to it, which I'll come to it. What is the relation of mathematics with the physical world or with the empirical world? Whether truths of mathematics are truths of the empirical world. So that's also a question. But if we these broad three categories of mathematics, how they view these empirical truths within the domain of how we can pursue analytical, how we can prove analytical or synthetic statements. So why is this analytical or synthetical statement important? Because whether there are axioms or whether there is a propositional logical axioms, whether there are propositions, prior propositions, the elementary propositions or axioms, which are the foundations of those statements, from which we have a deductive reasoning, and there is a we normally talk of demonstrative proofs are associated with those deductive reasonings. So that's it. So in the scheme of mathematical thinking, proving a theorem is that as an activity is more. So once you arrive at some theorem, they will give some religious sentiment is attached for mathematicians. This is what we got. So the process of thinking, so more or less mathematics as a mathematical way of thinking, as whether it's a logical way of thinking or whether it's an intuitive way of thinking or whether we formalize things. It's basically how we think, how we rationalize, how we think in a whether we impose rules of formal reasoning, whether our reasoning is intuitive, or whether logic is the fundamental edifice from which we can assume things. So there is a rigor, there is a consistency, and there is some thing which go into making And we have deductive proofs, deductive demonstrable proofs, which go into the making of how we construct mathematics. So this is much. So if I'll say, for example, so there are some statements to the effect. For example, we say, without saying how formalists construct mathematical truths, for example, formalists will say formalistic statements are synthetic and empirical. Synthetic and empirical, and intuitionists are synthetic and non-empirical. Got my point? Formal is synthetic and empirical, intuitionists are, and if I will add school of Leibniz, he was more logician. So for him, the synthetic, the analytical statements, they dissolve. The notion of analytic subject and predicate gets dissolved from the logical school.
I see.
So how we construct the empirical world vis-a-vis these statements? So there are different fundamental underlying assumptions that if you have a synthetic statement, there is more than the fundamental premise. You can add something. So what you want to add, whether that's intuitive or that is in the world. So it stems from the empirical part of the thing, or it stems from the prior intuition. So there are different there are different what I should say opinions about the same. So the point to mention is that once a mathematician, so when we say mathematics as an activity is more how we can think, how we are able to think, or how we are able to deduce things from. Now I am going to what I am going to do. So this is the base of this thing. Now, and you can say that, for example, you can also, if you add statements of Plato in it, for example, for Plato, mathematics is all about forms.
Okay.
And Aristotle could not adopt Plato's theory. So, for Aristotle, mathematical statements are necessary. They are descriptions of eternal and independently existing forms.
Okay.
So what the thing which I am going to, this is the background thing which I am going to say. So I'll just write a couple of statements and just supply some logic to those statements in some sense, in the background of what I have said. So, first statement is the concept or content of geometrical statements statements is determined by totality of axiomatic systems coupled to logical deductions or inferences with reference to empirical to physical or empirical universe. So,
Can you repeat it?
so the concept of content of, well, not because I have said that mathematical, maybe I'll just use mathematical, then see it's the case for geometrical statement that it becomes more pronounced, this distinction here. So here I have just changed the word. So concept of contempt of mathematical statement is defined by totality of axiomatic systems. The total axiom systems is determined by that, coupled to logical deductions or inferences, with reference to physical or empirical universes. This is as clear. So you just formalize an axiomatic system. You have logic to those, whether it's deduction or induction, and it is done while taking into consideration the empirical world or the physical part of the universe.
Maybe they are physicists doing mathematics, or mathematics.
Exactly. Now there can be various. I would say there is nuances to it.
Okay.
So it is what you are saying, but it's not exactly what you are saying. You got my point. So there are subtleties which I'll just try to make point. For example, if this statement here I use more geometry, that will become more clearer. If it's not mathematical statements, if they are geometrical statements, there are some things which will come into consideration. For example, this understanding has to be, for example, supplemented. If they are not mathematical statements, if they are geometrical statements, so if it has to be supplemented by normative function of visualization. What do you mean by that?
Normative
function of visualization, which is not per se usual, but justified from logical origins.
Wow. Just
You got the point. So you have to solve this norm. So once we have any geometrical statement, this space, so we also have this thing. It's also physical. You can see it. So geometrical statements also are empirical statements. If you remember the last time I also said that it's a loaded term, empirical. So if geometrical statements can be had from an empirical intuition or visual intuition, but we have also logical. So if, from axiomatic system, you can from deductive or inductive reasoning, you can reach from where you started. Even if you have imposed formal reasoning. So even if you have visualization from physical space, but it has roots in empirical thing. Yeah. Now I'll come to part of the other part of it. So mathematicians have been, if you remember, we have Euclidean geometries and mathematicians working in non-Euclidean geometries. Or Euclidean geometries, So once we made this jump, or once we made an extension from Euclidean geometry to non-Euclidean geometry, so that fifth postulate can exist independent of the other postulates. So it's an independent, consistent system which is equally logically viable. The sort of intuition, visual intuition, is not necessarily hard and fast. So in non-Euclidean geometry, so we take recourse to logical statements rather than statements of visualization. Because we can alternatively formulate other geometries which are equally consistent.
So they need not to be empirical.
You need not to also supplement it by that visual thing, which is empirical in its manifestation. You got my point. So working on, so this is a jump from from Euclidean to non-Euclidean geometry. So people took recourse to logical relations of these, you can say, artificial manifolds if you want to say. Artificial in the sense that you can construct it. So maybe whether they manifolds or prior again. So if you can construct it, you can say it. Now here comes the point. The point is that this is the third point. This is the fourth point. That the question is now. The question is what? Question is whether correspondence of mathematical or geometrical statements, mathematical or geometrical statements, constructions, depends on not on inner a priori, not on
Inner a priori means?
means you have a construction of geometry which you can assume, you can deduce from logical assumptions, but it has some correspondence to that physical world.
Oh.
So a priori constructions of geometry,
They can be empirical as well.
they are empirical also. This is a statement.
Okay.
You got my point. So the question is this inner a priority, how can it be justified? So is it there something called principle of harmony and symmetry? So if you read it, there is a famous essay by Helmholtz on origin and significance of geometrical actions. So in the last sentences he says this, or even people like Emil Kant, also they have this prior harmony of what exists and what we are going to observe. So nature is what should unfolding in some subtle way.
Wow.
That so these are statements of Helmholtz, this Emil Kant, and Einstein also says that when he says that the most incomprehensible statement, think about the universe is that it's comprehensible. So it's also echoing that thinking. You got my point. So, but you can root it here, these mathematical and geometrical statements. Now comes the physics part of it, or the empirical part of it. The empirical part of it is like the fifth statement is physics is concerned with questions which geometry is simple.
Which geometry
is simple. Or simpler. Or convenient also, you can say, which will relate to the physical world which we are.
Why it has to be simpler?
So this is also a big thing, epistemological construction, whether it has to be simpler or not. Normally, when we talk of harmony, when we talk of symmetry, from this, for example, visual circle is the most minimum parameters.
This follows as Dirac and other people. Beautiful equation.
Yes, this is symmetry. You have this least number of parameters to describe the system. So you can, it stems from this thing. It's not necessarily, it may be, we should believe in symmetry or something. So that's why the point is that epistemological a priority cannot be maintained. Because once we construct geometries which were non-Euclidean, or you can construct as many geometries as possible, it's not necessary they will which physical phenomena they can map to, and so the a priori, so it becomes suspect. Epistemological a priori becomes suspect. You said which also why should be simple? So why should nature be simple? Or why should you construct a geometry which should have a simpler mapping or complex mapping? So you become, this thing becomes suspect. Now I come again back to my idea of synthetic and analytical states. So if you frame this thing in terms of synthetic and analytical statement. So we can say, if we reframe it in terms of synthetic and analytical statements, we can say these concepts or these, if we frame in terms of analytical and synthetic statements, which correspond to those propositions or those axioms which have those subject predicate relations, and from which we can have analytical or synthetic statements, from which we have those truths of fundamental things. So these concepts are applicable only to sentences which can be true or false, not definitions. Got my point? So once you have propositions and once you have logic attached to it, you can have Boolean algebra, yes, no, or you have a definitive answer. Categorically, you can say syllogism. Whether this exists, this is right, this is wrong, this is what. So you arrive at some statement, you should come back to what started. So in terms of on and off statements. So they are not applied to definitions. Definitions means if we give those primary propositions some adjectivity, something which is more than those, they are not dry, they are not, for example, points are no color, length, line is only two. So we don't have adjectivity attached to those prior assumptions. So if they are not assumptions, they are definitions. So then this truth, this categorization has some problems.
There seems to be a correspondence, okay, maybe in our mind at least, in the formalism, within the formalism, between assumption and definition. Sometimes our assumptions become our definitions.
Or assumptions become our definitions, yes, exactly. But once you go to analytical and synthetic statements, you are very strict in what we assume as propositions and what we can deduce. What are the theoretical deductions or inductions. So you start from A to B to B, so that's strict and that's clean.
But if you are particularly focusing in the analytic, as you are saying, as I can gather, I can be wrong, interested in the chain that happens between those propositions.
Exactly.
Not in the proposition itself.
Not in the proposition, that's what I'm saying.
So whether they are assumptions or definitions, it doesn't matter. It's a secondary question.
But if you assume they are really definitions, then there's a problem. So these definitions, what these definitions will have is that these definitions have, for example, these definitions have antecedents in what? In axioms, which are reasonable statements.
Have
antecedents. They have roots in those axioms, which are reasonable statements in the sense that evolved also by special visualization. Apart from logic imposed upon them, which is clean, they can also be evolved by special visualization. Whose individual content is based on convenience, so what is the content of those definitions is made malleable, to suit ultimately what we physical think you are going to observe. So it's based on convenience. So this truth content of statement, everything a mathematician has a perfect, when he says the element of proof I have discovered, it's somewhat true. He has faith, so it stems from an eternal belief in truth of mathematics. But it can somehow be shattered in some sense. So when you say it's based on convenience. So if you add empiricity to the statement, And the logic of convenience to it. For example, Poincare said why I chose non-Euclidean geometry is not because it explains some facts more, not that it is true. So here, here maybe different mathematicians will have.
I think this is very important. Can you just touch on it more?
So here it's a matter of different mathematicians may have different opinions to it. For example, what you are going to map and what are the logical and propositional logic and the formal logic and the deductive reasonings we are going to have. So the mapping to the empirical and this thing. So how much it's valid as an exercise also.
Basically,
So some physicists or some mathematicians take it as serious. This is something. The Platonic constructions are eternal forms. So what we are going to discover? So physics is the abstraction of lower level of what mathematicians were discovering mathematics. Physics is discovering mathematics. But this is one thing. If you go in a serious way, if it's not convenience. If it is convenience, then it's all becomes so the meaning of truth content. It's also not that hard and fast. It depends. So that's it. So now here I'll just say that this thing. That only logical statements, like only logical statements or symbols have independent meaning. Geometrical statements have derived. So statements have derived meaning in the sense that if we have an element of visualization involved in them, so they will have. So here, as I mentioned, if you read Frege and Hilbert's correspondence, where Frege wanted that logic and the truths of geometrical statements, he says that we have to give meaning to the symbols. After, not Hilbert says that we give meaning to symbols after we formalize the things. For Frege, we first give meaning to the primal symbols, then we deduce. So there's a subtle debate to it. But the point I want to make is that logical statements have an independent meaning, and geometrical statements can have derived meanings. So axioms of geometry are guaranteed by special intuition, which are at the base of those structures in that sense. So other viewpoint maybe, so if is that other viewpoint is that we can criticize, we cannot criticize axiomatizing geometry or formalistic view of Hilbert. We can criticize it. Maybe there have been mathematicians to that effect, just or of the opinion. So special intuition is required to establish axioms of geometry and not those of arithmetic. Now geometry is not as basic as, from this we can have it, this thing.
Geometry is not as basic as
logic or arithmetic. So you can just
clear.
But in our times, we don't talk of geometry, we talk of topological space. We have used notions like non-geometrical space, we have topological constructions or topological space or manifold, and we have relations in algebraic topology, how we just understand. But the underlying point I want to mention is that again, the question still remains, which I just tried to say in some subsequent statements, that geometrical statements as self-evident truths assume geometrical facts are simple and obvious, and their validity is assumed. Their validity is assumed. Or from this, you can also say that using geometry as a, even if use geometry as convenient and more convenient to construct geometrical or topological space being unifying factor. So algebra could be understood as a highly developed logic. Algebra could be understood as highly developed logic. Now, this was a bit sense that. So I just jump to physics part of it. So how we can the empirical part of it? It's a big discussion. So how we can judge scientific theories? So maybe this is entire thing. So I just slightly just pondered because it needs a separate lecture. So what is the how can the desiderata of scientific theories? What are the basic
standards maybe?
we normally talk of simplicity. If you just see the literature, we talk of unifying power. We talk of explanatory power. And some people also see a fertility. Fertility not in that biological sense, fertility in the sense of, it's also in biological sense how much you can reduce or how much, in the sense of how can you explain the variety, how much you can explain things from a given theory or from given prior assumptions or from the theories which derive their validity from those propositions and from which we logically deduce things. And those assumptions are priorly constructed or they are constructed posteriori from the empirical world. No, they are priorly constructed not, or whether they are synthetic or analytical statements. And the assumptions, and once we just induct them with some physical things, how the system gets constrained with the addition of data, whatever we can say it. So I'll just end this lecture on this note, maybe, of something called, so entire this thing was that whether mathematics is intuitive, whether it's formal, whether it's logical, and how these three things are dealt with, how we construct the world as empirical. And when we talk of empirical, we talk of the construction of physicists, chemists, how we see world. So there comes a minor subtle point. So there is a branch of mathematics that's called as constructive mathematics.
Constructive.
So basically people from Russians maybe have more, they might have, or now there are school. So they are interested in this question. For example, you might have heard the name of Lev Landau. Have you heard of him? He's a physicist. Maybe what? Landau.
Lev Landau.
So there was another Landau, you might have not have heard of his name. He's also Landau. But he was an analyst, a mathematician. Landau not the physicist, Landau the analyst. So Landau the analyst went to Landau the physicist. No, or they were saying what Landau the physicist was saying, what are you doing? He was saying something. So he gave him some problem in some part of physics. And the Landau, the mathematician, the analyst came after some days or month or so. He came with a thick thing and he said, I have solved your problem. So I find that your solution is a set of partial differential equations and I have found solutions to your differential equation. So for him, solving a problem was how he translated that physical problem to his own mathematical formalism of partially finding a solution to that differential equation. So for him it was, so here again we can, so either mathematics is an activity of generating theorems or results, or it's a process of forming the solutions. So it's not interested in the physical part of the world. So maybe this question of how we can categorize applied mathematics, theoretical physics, problems of applied mathematics, which stem from how you construct pure mathematics, which deals with these formal, logical, intuitive, abstract structures and the logic, and how we can construct that with regard to the how an applied mathematician is more in what I should say is more has a methodology where he is more interested in being faithful to his those prior constructions and generating solution with reference to that rather than what is he observing in the world. For a theoretical physicist, he has some physical problem, turbulence problem, atmosphere problem, physics problem. So this attitude and this attitude. So I'll say that that how we can relate these different domains, how we can construct mathematics and different schools of mathematics, and how we can construct them, relate them with the physical part of the world, and whether the constructions can be interchangeable or not, or there are some fundamental limits to it. Those forms. I have not talked of in some lectures how modalization, also the formal part of it, how we formalize arithmetic systems, how the modalization shows that it's incomplete, and what it leads to, the understanding of mathematics it leads to. So that's it. So that's another part of the story, the limits of formal methods in axiomatizing or formalizing arithmetical systems, and how it has an imposed understanding of how mathematics and different schools of mathematics as such. So that's also a relevant question, and how that question is related with other questions, and how that is related with the empirical questions. So this is also an interesting story. Maybe I think I have tried to convey the flavor of today's lecture.
Yeah.
So should I stop?
I have a question. I mean, I have lots of questions, but there's one question I want to ask as for now. As you mentioned, there are broadly three schools of thoughts: mathematics, formalists, intuitionists, and logicists. So, what is the difference between the three, or particularly formalists and logicists? Because I feel making a formalism requires logic as well.
But it requires logic to different degrees. For example, logic as an end in itself, and logic as a means to end. These are two different things. So you want to read something, you have a skeleton, but you leave those clothes. Like child is there. So you want to enter, you go to quantum mechanics, you use formalism of classical mechanics. But then once you are in quantum mechanics, you leave formalism. You say that it was only merely a tool to reach somewhere. Logic as a tool and logic as an end. So here, so formalists use logic as a tool to generate.
Logicists say this is.
So they are more interested in formalizing the structures, formalizing this proposition.
And that formalism, that structure is important.
Important for them. And once you go give definitions to those structures, so whether the statements remain analytical or synthetic. For logicians, they will be analytic. For intuitionists, they will be synthetic.
Or it has to be.
No, but there are degrees. For intuitionists and formalists, synthetic, those prior assumptions may be synthetic. One in the intuitive sense, and other in the empirical sense.
Right. So let us clear this one thing. So, what formalists basically do, they use logic as a tool, and then they make the formal structures. And those formal structures are important, and with relation to vis-a-vis synthetic and analytical statements, synthetic statements are more valuable to them.
Synthetic statements may contain analytical statement and more to it.
But for logicists, they are more inclined towards analytical statements.
Analytical statement that subject and predicate are one unified whole. There is nothing outside it. So you have a strict definition and you have a strict. So there is not An analytical statement will contain a predicate and what you can derive from that subject and predicate. And so it's a whole system. It's a well-contained, tight system.
And one step further, we can have an understanding now whatever we have got, whether it is intuitive or empirical. That is the next step.
The next step is whether the logical constructions
Or formal construction.
formal logical constructions, whether they encompass the empirical world.
Or they intuitive or both at the same time.
Yes.
And there are three possibilities, or the intuitive, or the empirical, or both.
No, these three questions comes, what is the ultimate reality from which you can construct the basic thing. If logical statements are the be all or the end all statement. So even though you can say that this formalization of Boolean logic, it proves that we cannot formalize the systems logically to the first things. So it has shown some defect in that thinking. But the question is that if you want to include as world as an empirical world, so the logical and empirical constructions are sufficient to describe the world. But if world is not entirely empirical, then you have to say that you have world intuitive, but you can have some part of logical and empirical world can be incorporated in those intuitive constructions a priori. A priori, you can say. Not posterior.
Yeah, I got it. Thank you so much. You cleared this part.
Okay. Will you stop?
Yeah, thank you so much.